Top 10 gemstones found where life couldn't survive. Some crystals are born in beauty, others are born where no life has ever existed. Deep beneath the Earth's crust, inside radioactive fault zones, sealed salt caves, and meteorite impact scars, some gemstones have emerged from places where biology has never touched, and never will. These are no ordinary minerals. They did not form over time in calm geological conditions. They were formed through extremes, exposed to temperatures above 2,000 degrees Celsius, and environments lacking oxygen, pressurized water, or the ability of microorganisms to survive. In this TOPS documentary, we examine 10 scientifically verified gemstones, each tied to a location where no living system could have existed during or after their formation. Their chemical properties reject life. Their isotopic profiles confirm isolation. Some are sealed in controlled vaults, while others have only been discovered from impact glass or interstellar debris. This is not a story about what has been found. It is a record of where life ends and something else begins. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we start. Ranked 10th, Zektzerite, crystallized in an alkali void. No water table flows through the peralkaline granite of the Pacific Northwest's dry mountain range. Vegetation is nearly absent, and soil development never progressed beyond shallow mineral fragments. The air itself carries a different dryness, less due to climate, more because the rock beneath resists any exchange with biology. Zektzerite, a lithium zirconium silicate, was first identified here in the early 1970s. Its formation requires an unusual convergence: silica under saturated melt, high concentrations of sodium and potassium, and a setting almost entirely devoid of calcium or iron. The host granite, known as nepheline syenite, rejects the conditions necessary for most common rock-forming minerals. The result is a geochemical isolation zone. Crystals appear as thin, tabular blades, ranging from pale pink to nearly colorless, and sometimes exhibiting weak fluorescence under UV light. Although stable at room conditions, Zektzerite decomposes above 700 degrees Celsius, suggesting it formed during the final phases of pegmatite cooling, when pressure dropped and incompatible elements had no other place to bond. There are no records of fossilized life in the formation. Ground surveys by the U.S. Geological Survey noted an absence of biological inclusions in the rock core. Field researchers classified the area as biologically sterile terrain. The mineral, by its very chemistry, cannot coexist with life-essential ions. Since its initial discovery, Zektzerite has only been confirmed from a single geologic complex, the Golden Horn Batholith in Washington State. All other attempts to synthesize or relocate it have failed under natural settings. Its status in mineralogical databases remains as site-restricted pegmatite terminus phase. Specimens are now held in curation vaults at the Smithsonian and the University of British Columbia. No further mining permits have been granted since 2002 due to ecological erosion risks. Field access remains restricted during fire season. Zektzerite's presence is not evidence of an ecosystem. It is evidence of what happens when the Earth cools past biological thresholds and chemistry continues alone. Ranked 9th, Painite, stabilized in a tectonic pressure scar. The upper crust of central Myanmar has never settled. Its geological record reads as a continuous collision: oceanic plates forced beneath continental margins, uplifted crust, folded and fractured beyond stability. The Magmatic metamorphic belt, where Painite was first discovered, records metamorphic episodes spanning over 400 million years. No persistent soil layer has formed. Biodiversity in the fault core remains among the lowest per square kilometer in Southeast Asia. Painite's composition, calcium zirconium borate, requires 3 incompatible trace elements to stabilize: zirconium, boron, and rare earth lanthanides like yttrium. In most crustal conditions, these elements do not co-crystallize. The likelihood of all 3 entering a single mineral phase is statistically negligible. Only under conditions of extreme temperature fluctuation, high pressure, and residual boron-rich fluid saturation does Painite become thermodynamically favorable. The original sample was misidentified as ruby in 1952, and it took decades for crystallographic analysis to correct the classification. Since then, fewer than 1,000 verified crystals have been found, mainly as fragmented prisms within spinel mica schists or calc-silicate rocks near the metamorphic contact zone. Painite-bearing rocks are geologically young but chemically chaotic. The Mogok terrain underwent repeated crustal melting during India's northward collision with Eurasia. Isotopic dating of zircon inclusions in painite samples suggests rapid cooling after fluid-rich injections, suggesting hydrothermal pulses along active faults. No fossil assemblages are preserved in adjacent strata. Ambient conditions during crystallization, high in fluorine, low in oxygen, are classified as non-biocompatible. There is no known biological process that mimics or assists in the formation of painite. No secondary growths or biological overprinting have been documented on crystal surfaces. Raman scans show clean lattice signatures, unaffected by organic acid weathering or biofilms. Current recovery is limited to select shafts controlled under Myanmar's Department of Mines. No commercial synthesis exists that replicates its lattice under atmospheric pressure. International gemological institutes list painite as natural only, with no synthetic analog registered as of 2025. Painite is not simply rare. Its formation signals a moment of crustal instability when incompatible chemistries align for minutes or hours at most, then sealed in a tectonic scar too hostile for life to anchor. Ranked 8th, Benitoite, crystallized in a subduction residue field. Between the Pacific Plate and the North American continental mass lies a suture that has long since ceased to move. The tectonic closure left behind serpentinized seafloor, pressurized fragments of oceanic crust, and isolated boron-bearing fluids that had no further pathway to escape. This is where benitoite formed. It was first recognized in 1907 near the headwaters of the San Benito River in California. The host rock is natrolite vein glaucophane schist, derived from high-pressure, low-temperature metamorphism, a signature of blue skies facies typically associated with ancient subduction zones. Such geological zones preserve almost no evidence of biotic activity, as they were formed well below habitable crustal levels and later abducted onto land. Benitoite requires a narrow thermal range and a specific chemical environment, one that is barium-rich, silica undersaturated, and low in iron. It is classified as a barium-titanium cyclosilicate, a structure not stable under most near-surface conditions. The mineral only stabilizes after the host rock has been locked against further heating or deformation. Once formed, the crystal remains unchanged. No known weathering products or replacement phases have been observed in the field. When exposed to shortwave ultraviolet light, benitoite fluoresces blue-white due to its trace manganese content. This photoluminescence is physical, not biological. No microbial residue or interaction has ever been documented on samples retrieved from the Dallas Gem Mine, the only known commercial source of gemstones. Soil samples in the immediate extraction zone have tested sterile in multiple biological assays. In 1985, California designated benitoite as its official state gemstone. Despite that status, it remains commercially marginal. Recovery rates are low, veins are thin, and the surrounding terrain, marked by landslide-prone slopes and eroded serpentinite, limits industrial expansion. A few permitted collectors still access surface scree, but the number of new finds has declined sharply. In current mineralogical records, benitoite is listed as a pressure-locked phase mineral, formed only during a narrow tectonic event window that can no longer be replicated. The region it comes from is tectonically extinct. No further crystals are expected to form unless plate motion resumes along a dormant fault line. The specimen's optical beauty is well known. Its environmental history is not, but both are permanently embedded in a fault trace that has long ceased to support geologic or biological motion. Ranked 7th, Ekanite, a crystal that self-destructs over time. The mineral structure of Ekanite cannot remain intact indefinitely. Its internal decay is measurable, visible, and irreversible, a result of its atomic instability. This property, known as metamictization, is not caused by environmental stress, but by the breakdown of the radioactive elements within the crystal itself. Discovered in 1953 by F.L.D. Ekanite on the northeastern coast of Sri Lanka, Ekanite occurs in cyanitic pegmatites, igneous rocks enriched in thorium and uranium. These host rocks are located in metamorphic terrains that have undergone repeated thermal overprints, and they do not support the development of complex ecosystems. In situ, samples from Trincomalee show high radiation levels relative to background counts. The surrounding zones are geologically active, but biologically uninhabited at the subsurface level due to persistent alpha radiation fields. The mineral's chemical formula includes thorium, uranium, and calcium silicate. Over time, the alpha decay of thorium and uranium nuclei damages the crystal lattice, disrupting optical clarity and shifting the structure from crystalline to amorphous. This process has been documented using X-ray diffraction and is considered irreversible under natural conditions. Gem-quality Ekanite is extremely limited. Transparent specimens have only been recovered in shallow alluvial deposits, where weathering temporarily concentrates small, stable fragments. However, prolonged exposure leads to a gradual loss of birefringence and color saturation. For this reason, most international mineralogical databases classify Ekanite as metamic prone. There is no evidence of biogenic interaction in or around the crystal. Unlike minerals that exhibit secondary alteration due to microbial or organic processes, Ekanite's decay is internal and inorganic. No fossil inclusion has been observed within any known specimen. The surrounding rock matrix also lacks trace carbon or nitrate signatures, which are typically associated with life in soil-based environments. Because of its radioactive properties, the handling and storage of Ekanite are regulated in many jurisdictions. Specimens exceeding a certain mass require shielding or documentation of decay. There is no known method to reverse metamictization once it begins. No lab synthesis of structurally stable Ekanite has been reported under ambient pressure conditions. Current samples are stored in mineralogical institutes under low-light conditions, sealed to limit structural deterioration. Despite its silicate backbone, Ekanite is categorized under actinide-bearing disordered phases due to its long-term atomic instability. Its classification is not based on rarity or appearance, but on the fact that left alone, it will destroy itself. Ranked 6th, blue halite, stabilized in anoxic brine cavities. Crystalline halite forms in evaporative environments where water volume declines faster than salt can be removed. When conditions persist for thousands of years without freshwater influx, the system becomes chemically sealed. In these zones, microbial activity declines until all oxygen is consumed, leaving behind anoxic brine, a hypersaline, stagnant, and uninhabitable environment. Blue halite develops deep inside salt domes under those exact conditions. These halite masses are often buried more than 1,000 meters beneath the surface, and their color is not a result of pigmentation or mineral inclusions. Instead, the blue hue is caused by defects in the crystal lattice, vacancy sites, and trapped electrons resulting from prolonged exposure to natural radiation. These defects alter light absorption properties, causing the halite to appear blue. The most stable blue halite samples originate from salt mines in Poland and Iran, as well as from deep domes in the United States Gulf Coast Basin. Temperature, brine saturation, and absence of oxygen must remain within a narrow range for the color center to persist. Minor changes in environment or exposure to humidity cause rapid fading, making long-term preservation a challenge. No higher-order life has been observed in these salt cavity systems. Anaerobic halophilic archaea exist in shallow halite environments, but viability sharply declines with increasing depth, salinity, and age. In crystal samples dated beyond 100,000 years, no traceable biological DNA or metabolic residue has been recovered. Scientific interest in blue halite has focused on 3 domains: lattice radiation studies, fluid inclusion dating, and extremophile survivability experiments. As of 2024, no viable organism has been cultured from any inclusion inside deep blue halite specimens recovered from pre-quaternary domes. Commercial extraction is minimal. Blue halite is brittle, water-soluble, and prone to desaturation upon exposure to air. Its fragility has excluded it from use in jewelry or architecture. Most samples are stored under nitrogen or vacuum-sealed display cases in mineralogical collections. There are no known environments on the Earth's surface today where blue halite forms naturally. Surface evaporation ponds, while producing colorless halite, fail to reproduce the radiative conditions required for electron trapping. The crystal's presence is not a marker of ancient life. It is the record of its absence. Ranked fifth, Olivine. Carried from the mantle through a magmatic breach, the continental crust averages 35 kilometers in thickness. Below that lies the upper mantle, a region where temperatures exceed 1,400 degrees Celsius and pressure routinely surpasses 13 gigapascals. No photosynthesis has ever occurred there. No microbial colony has been observed. The geologic record contains no evidence of organic activity beyond the Moho discontinuity. Olivine, a silicate mineral composed primarily of forsterite and phyolite, constitutes the dominant phase of the upper mantle. It crystallizes under high-pressure, high-temperature equilibrium in peridotite and dunite matrices, rock types that remain inaccessible without deep magmatic transport. When mantle-derived magma breaches the crust, it can entrain fragments of mantle rock, known as xenoliths. These xenoliths are chemically distinct from crustal rocks and frequently contain unaltered olivine crystals. Their arrival at the surface is rapid and often violent, preserving high-temperature features that would otherwise recrystallize during slower ascent. Olivine from xenoliths is frequently fractured, rimmed by serpentinization halos, and partially altered due to decompression. Yet in rare cases, gem-quality olivine, classified as peridot, remains stable enough to retain transparency. These specimens are primarily sourced from volcanic fields in Arizona, the Canary Islands, and Siberia, where fast-rising alkali basalts intersect with mantle lithologies. No xenolith sample has yielded organic inclusions or secondary biogenic alteration. Analysis of fluid inclusions within mantle olivine reveals compositions high in carbon dioxide and incompatible elements, but no organic acids or microbial signatures. Thermodynamic models confirm that olivine's stability field exists entirely outside known biospheres. From a crystallographic standpoint, olivine's orthorhombic structure is mechanically efficient. However, it is chemically fragile when exposed to atmospheric water. Surface specimens decompose within decades. Subsurface samples remain intact only when encased in host basalt. Modern imaging, utilizing Raman spectroscopy and electron backscatter diffraction, has confirmed that olivine and mantle xenoliths records deformation histories dating back up to 3.5 billion years. These samples contain no trace of surface exchange. Peridot specimens sourced from xenoliths are now archived in controlled humidity storage at National Geological Collections. Their scientific value lies not in their aesthetics, but in their origin, a depth never reached by biological systems, preserved only through the force of planetary rupture. Ranked fourth, Hibonite, preserved from a time before Earth had crust. No terrestrial material can match the isotopic composition of specific inclusions found in meteorites. These inclusions, rich in calcium and aluminum, represent the first solids to condense from the solar nebula, approximately 4.567 billion years ago. Among them is Hibonite. Its formula, calcium aluminum 12 oxide 19, corresponds to a high-temperature refractory oxide phase. It forms only in reducing environments with elevated temperatures exceeding 1,700 degrees Celsius, conditions that no known planetary crust maintains. Hibonite does not crystallize from molten rock on Earth. It forms instead through direct condensation from vaporized dust in protoplanetary space. Hibonite is most often found as angular, sub-millimeter grains embedded within CAIS, calcium aluminum-rich inclusions, inside carbonaceous chondrites. These meteorites are classified as unaltered, undifferentiated relics from the early stages of the solar system. Their matrices are chemically hostile to organic preservation, being low in water and volatiles, and frequently rich in spinel, perovskite, and facite. No biogenic structure has ever been detected in a Hibonite-bearing CAI. Carbon isotope analysis consistently yields delta-13 C values incompatible with organic synthesis. Laboratory simulations attempting to synthesize Hibonite under Earth-like conditions require inert atmospheres and controlled furnace cooling profiles, which are not found in nature. Most confirmed Hibonite samples originate from meteorites recovered in Antarctica, specifically the Allan Hills region, where slow glacial movement preserves micrometeorites for long periods. Other finds include the Murchison meteorite, Australia 1969, and the Allende Fall, Mexico 1969. These samples have undergone rigorous scanning electron microscopy, electron probe microanalysis, and noble gas retention tests. Because Hibonite is one of the first solids to crystallize in the solar nebula, it is also one of the most isotopically anomalous. Some grains contain extinct radionuclide decay products, including the short-lived isotope 26 aluminum, which provides time-stamped formation windows that are no longer reproducible. Its structure is stable, its origin is extraterrestrial, and its formation predates Earth's differentiation into core, mantle, and crust. No known living system has ever interacted with it. In classification terms, it is a prebiotic phase solid, and its presence in meteorites marks the absence of any biogenic influence during or after its formation. Specimens are curated in isolation chambers, primarily for cosmochemical study. Their value lies not in color or clarity, but in chronology. Hibonite is not from a world where life couldn't survive. It's from a time when life hadn't begun to try. Ranked third, Trinitite, melted into existence at 4,000 degrees Celsius. At 5:29 a.m. on July 16, 1945, a detonation equivalent to 21 kilotons of TNT introduced conditions to the Earth's surface that had never naturally occurred in recorded geologic time. The location, Jornada del Muerto, Desert Basin, New Mexico. The test, codenamed Trinity. At ground zero, sand composed of quartz, feldspar, and trace minerals underwent instantaneous melting, forming an amorphous greenish glass now known as Trinitite. The formation of Trinitite occurred at temperatures estimated between 1,600 degrees Celsius and 4,000 degrees Celsius, exceeding the melting points of silica, alumina, and most terrestrial rock-forming oxides. Vaporization and recrystallization occurred in milliseconds. The resulting glass solidified under conditions of extreme ionization, partial atmospheric vacuum, and neutron radiation flux. No biosignatures have ever been found in Trinitite samples. Pre-detonation soil cores, preserved by the U.S. Army Corps of Engineers, contain trace microbial carbon. Post-detonation samples show none. Immediate radiation levels within the first 24 hours were lethal to all known forms of cellular life, with measured gamma doses exceeding 25 sieverts at the surface. Trinitite is a silicate-based glass. Its structure is non-crystalline, consisting of irregular oxygen-bridged tetrahedra embedded with metallic spherules of iron, zinc, and copper vaporized from the test tower infrastructure. Specific variants, including red Trinitite, contain inclusions of copper and semiconductors from destroyed instrumentation. The radioisotopic decay of cesium-137 and americium-241 remains detectable in some specimens, although most have now decayed to background levels. Recovery of Trinitite was prohibited shortly after 1952, following concerns over residual contamination and preservation of the site. All legally held specimens originate from collections acquired before the moratorium. Unauthorized collection from the site is prohibited under federal law. Trinitite is anthropogenic and non-reproducible. No experimental furnace has yet replicated its complete structure under controlled conditions due to the difficulty of mimicking fast-cooling, high-radiation melt environments in open air. Mineralogically, Trinitite does not qualify as a naturally occurring gem. Its inclusion in scientific catalogs is conditional, as a verified product of nuclear melt chemistry. It is not graded for color, clarity, or brilliance. Its value is historical, not gemological. No ecosystem has regenerated in the core of the immediate blast zone. Remote sensing imagery and soil biology surveys confirm that microbial recovery remains partial, even after 80 years have passed. Trinitite exists as a single event phase, crystallized in a zone sterilized by human intervention, at a temperature that no organism could survive. Ranked second, Tektite, formed in seconds in a zone of total erasure. When a high-velocity meteorite enters Earth's atmosphere at supersonic speed, friction and compression are not the only forces involved. Upon impact, the kinetic energy is converted into heat, enough to vaporize bedrock. The resulting temperature exceeds 2,000 degrees Celsius, forming a plasma envelope that radiates outward in a hemispheric shockwave. In that moment, no terrestrial environment survives. Tektites are the condensed ejecta of such impact events. They form when terrestrial silica-rich material is melted, vaporized, and then expelled into the upper atmosphere, cooling rapidly into natural glass as it re-enters under low pressure. The entire process, from impact to solidification, takes place in under a minute. Tektites are chemically homogeneous, non-crystalline silicate glass. Their structure lacks internal water and contains minimal volatile inclusions, suggesting formation in a vacuum-dominated thermal regime. Trace element analysis reveals depletion in alkali metals and enrichment in refractory oxides, indicators of high temperature, low pressure differentiation. Distribution zones, known as strewn fields, cover thousands of kilometers. The Australasian field is the largest, spanning from Southeast Asia to Australia. Others include the Central European Moldavite zone and the North American Bediacite zone. Despite their wide dispersal, all tektites from a given field derive from a single impact event, each marking a geologic surface that was instantly sterilized. No tektite-bearing layer in any region has yielded evidence of unaltered biological sediment. Stratigraphic sections across strewn fields consistently show a sharp boundary layer characterized by shock-metamorphosed quartz, carbon spherules, and glass shards. The impact layer in the Czech Republic's Moldavite field corresponds to an extinction-level energy release, though not associated with a mass biological die-off. Tektites are not products of volcanic activity. Their lack of vesicular texture, high Le Chatelierite content, and aerodynamic morphologies differentiate them from obsidian or pumice. Flattened dumbbell and teardrop shapes indicate plastic deformation during atmospheric flight, not lava flow. Specimens exhibit no internal crystal growth. Under polarized light, tektites remain optically isotropic. No secondary alteration zones, such as hydration rims or microbial etching, have been observed in fresh specimens. Weathering occurs only through surface abrasion and chemical leaching after exposure. Tektites have been recovered from layers dated between 35 million and 700,000 years old. No sample recovered from any field shows signs of having formed in a biological matrix. All are associated with crater-generating impacts, events that instantaneously remove biospheres within their target radius. In current geochronology, tektites are categorized as impact-generated natural glasses, with formation temperatures, pressures, and timeframes incompatible with all known organic synthesis processes. They mark a geologic instant of irreversible erasure. When matter melted, life vanished, and glass fell from the sky. In first place, Moissanite, detected where planetary chemistry ends. In 1893, during a field study of the Canyon Diablo meteorite fragments near Meteor Crater, Arizona, French chemist Henri Moissan isolated a mineral with a crystal structure unlike anything previously observed in Earth's geology. He believed it to be a diamond. Years later, a corrected analysis identified it as silicon carbide, also known as moissanite. On Earth, silicon carbide does not occur naturally in crustal igneous, metamorphic, or sedimentary systems. It requires oxygen-poor, carbon-rich conditions under pressures and temperatures not attainable in terrestrial lithospheres. The formation environment of natural moissanite is now confirmed to be extraterrestrial, within carbonaceous bodies or differentiated planetary interiors subjected to high-impact metamorphism. Moissanite has been identified in iron meteorites, uralites, and lunar regolith breccias. It has also been located in shocked mantle xenoliths, but only where meteoritic influence is evident. Spectroscopic analysis reveals that these occurrences correspond to rapid crystallization from high-pressure vapor phases, which requires both extreme temperatures and the absence of atmospheric oxygen. The stoichiometric lattice of moissanite is highly ordered. It exhibits exceptional hardness, 9.25 on the Mohs scale, a high refractive index and thermal conductivity similar to that of diamond. Yet its relevance in geology is not its durability, it is its origin. Each naturally occurring crystal is tied to an impact event or an interstellar process. No biosignature has ever been recovered from a natural moissanite specimen. Its growth environment excludes the presence of water, volatiles, or carbon-based polymers. Electron microscopy of recovered grains shows no trace of organic inclusions, weathering, or microbial etching. The material is inert to biological interference and unaffected by oxidation over geologic time. As of 2025, no natural moissanite deposit has been discovered in situ on Earth. All confirmed specimens derive from meteorite debris, breccia zones, or impact ejecta Simulated formation requires chemical vapor deposition in controlled vacuum environments exceeding 2,000 degrees Celsius, replicating conditions only present during planetary collisions or stellar nucleation. In the meteoritical bulletin, moissanite is categorized as a pre-solar and impact phase mineral. Its isotopic ratios, especially those involving carbon and silicon, align more closely with interstellar grains than with Earth-based material. There is no location on Earth where moissanite forms independently. Its natural presence signals an event in which local chemistry failed, overridden by external force, speed, and entropy. Today, synthetic moissanite is commercially produced in laboratories, but its natural counterpart remains restricted to impact fragments and cosmic debris. It does not mark the edge of Earth's mineralogy. It marks the beginning of something beyond it. The gemstones featured in this documentary were not shaped by time, rupture, exposure, and environments beyond biological tolerance. Instead, these environments formed them. Each sample carries physical evidence of formation outside Earth's habitable range. No oxygen, no carbon cycling, no cellular legacy. Geologists do not classify these minerals by rarity or commercial value. They are defined by origin, structure, and the absence of organic interference. Whether retrieved from nuclear impact zones, meteorite layers, or mantle xenoliths, their presence confirms that conditions are too extreme for life to persist. What remains is not just inert matter, but a record of pressure, of radiation, of extinction. More than gemstones, these are crystallized data points, unambiguous, indelible, and still unread by most. Let us know which one resonates with you in the comments, and don't forget to like and subscribe to our channel for more content like this.